then postdoc at GSI in Germany, and then came to the States, where he was employed for a short time at Alamos National Laboratory, and then went to a better national laboratory, Argonne, as the staff member where he's been ever since. In that time, he worked on fusion dynamics, and since I've been in the colleagues on various things, studies of exotic phenomena in heavy ion collisions and various other heavy ion reactions. Also, we did a sojourn at Brookhaven National Laboratory, going up into the higher energy domain of relativistic heavy ion collisions, the Phobos experiment. But he has returned to denser air, lower energies, and today he's going to tell us about some of what's going on at Argonne National Laboratory, telling us a bit about radioactive beams at Argonne, and also a project that we're working together on, which is the helios spectrometer.
Thank you, Alan, and thanks for the invitation to come and visit and talk with you. It's very nice. And as Alan said, we've been collaborating for many years, so a lot of the work I'm going to show is collaboration with Western Michigan. But I'd like to tell you a little bit about the radioactive beam program at Argonne. I think it's quite timely. You will have after the road in about 10 years' time the world-leading facility in radioactive beams and what one can do with such beams. So it may be of interest, not only in nuclear physics, in other areas also. So this is just an outline of my talk. I'll talk a little bit. What is the drive? Why is it we want to start studying radioactive beams? And then the three methods that we are using at Argonne to generate these beams for studies of nuclear physics and natural physics. Two accelerator method, in-flight method, and the caribou that is coming online. And I'll talk about that in some detail. Then I'll turn around and talk about transfer reactions and what's the motivations about looking at those. And with radioactive beams, you have to do that in inverse kinematics, so I'll discuss that a little bit. And then we come up to talk about the spectrometer that we are jointly working on and how it's being implemented at Argonne. And I will show some early results. I'm not going to go a lot into the physics. It is still coming out. And in any case, I think Alan can give you a much better representation of many of these things. So this is the nuclear map. That's what we want to study. We have here the stable nuclei coming up, and they have been studied very well. But you will see there's another area here. These nuclei actually exist. They are open for study, but they do require radioactive beams to get out into these areas. On many of the on the proton-rich side, you can reach infusion reactions to study those nuclei. But out here, you definitely need radioactive beams. Why are we interested in this? Well, as I see it, there are two main reasons. We want to really understand atomic nuclei. And we have, as I said, we have started in this area here. Do those models really extrapolate out away from the line of beta stability? Well, we have some models. We have the ab initio body calculations that is being carried out at Argonne. They can really only scratch this little corner of it, then you run out of steam. Computers are not fast enough. Up to mass 12 or something like that. You have low-core shell models that extend up further, and this is an area that's been worked on very much by theorists, density functional theory. So these are the models that will help us understand these nuclei. But as we all know, that you cannot let the theories loose, you really have to keep them in check. That's why we want to go in with the experiments and check their predictions. And it's always a feeding forth and back between theory and experiments. So the other reason is that these nuclei way off the line of stability are very important for producing the atoms that are around us. We see all the day around us. They were not made in the Big Bang. They were made in explosive as physical processes, supernovas and so on. And some of these processes really take place out on the edges of this map. You have the rapid proton process going up in the proton-rich region. You have the arc process, rapid neutron capture that is believed to follow this line here way out in unknown territory. But of course you also have the S process, which is a slow neutron capture process. But that goes through the nuclei we already know very well. But these two other processes really need to be studied on the nuclei that are touched by those. And that again just emphasizes that we have the RP process here, we have the R process out in this area here. It is believed that the shell structure of nuclei plays an important role out here. You can see these waiting point areas. Again, that's theoretical predictions, and it has not been tested. We need to go out and test how well are those nuclei bound. Does the shell structure that we see near the line of beta stability really extrapolate out? And well, there's some indications that they don't. Down in relatively light nuclei, you can be surprised to find new magic nuclei that are especially strongly bound, and others that were supposed to be that are not. So the picture changes as you go away from the line of beta stability. You cannot just blindly extrapolate. And again, here you see the various models that come into play. And here, for example, you would like to study, in this case, tin nuclei over a very wide range of Newton number. This is where studies have been carried out using stable isotopes. And you see, for example, the distance between these two proton orbitals changes very drastically as you put more neutrons into the system. And you want to study further out, it plays an important role. So this is just a little bit on the motivation for this area of research. There are many other motivations, and this has all been compiled in long-range plan for the nuclear physics community. And this was just a few that I'm interested in. So let me get back to what we have been doing at Argonne over the last decade and a half. So we started out with this two-accelerator method, which is really very, very simple in a way. We have several beams that have been produced that way, fluorine 18, nickel 56, and titanium 44. And what you do, you produce the nuclei you want to accelerate at one accelerator, then you transport it to your facility, put it into the ion source, and then you make a beam out of it. Now, that only applies to nuclei that live fairly long. You cannot do that for one that lives only a few milliseconds or a few seconds. But then you can use this other method that has been used for about 10 years at Argonne. That's in-flight radioactive beam production. And these are all the beams that have been done. It's not all the ones that can be done. And I should mention here that Alan has been involved in many of these studies in light nuclei and physical processes. So what you do here, you bombard a target with some beam that you do have available. In the target, you make a reaction, a DP reaction, PN reaction. Now you produce a nucleus that is not stable. You capture that nucleus or that in a beam and transport it into your experimental area. I'll talk a little bit more about that. And then finally, well, it should have been 2009, it'll be 2010. We have a new method of using radioactive nuclei, actually some very interesting ones. And that is, we have this, we have a very strong, or we will have a very strong source of californium-252. Now, californium-252 is a spontaneous fission nucleus, so by itself it breaks up into two fragments. And those two fragments that come out in the fission are actually very neutron rich. They're not stable at all. And so by taking these fragments, slowing them down, mass analyze them, and finally accelerate them, you get some very interesting neutron rich nuclei that are out in the region that you want to study. And then finally, as I mentioned before, in about 7 to 10 years up the road, there will be FRIP on this side of Lake Michigan that will be the world's leading facility for radioactive beams. So this is an old slide from Strain, who came up with this method. So as I said, you accelerate you do a PN